Okay, in this video I'm going to continue on with my tutorials on thermodynamics and statistical mechanics. This is video number 43 and I'm going to discuss the chemical potential of an ideal gas. I'd like to draw your attention to my website universityphysicstutorials.com. The previous video to this is number 42, where I discussed the relationship between the Gibbs free energy and the chemical potential. And what we saw is that the Gibbs free energy per particle is equal to the chemical potential. So just a bit of revision to include video number 42. What we saw was that dg is equal to mu dn. So of course when we integrate that we find that the Gibbs free energy, total Gibbs free energy, is the chemical potential times the number of particles. So that's why we said that the Gibbs free energy per particle is the chemical potential. Alright, so going back to our thermodynamic identity for the Gibbs free energy, we find an infinitesimal change in the Gibbs free energy is minus S dt plus P dV plus mu dn. So just let's look at some of the partial derivatives we have here. So we know of course that del G, del N, okay, is going to give us the chemical potential. But if we look at del G, del P, we're going to get the volume. And you'll see in a moment where we're going to use that. So going back to our relationship between the Gibbs free energy and the chemical potential, or the chemical potential's role as the Gibbs free energy per particle, we saw that G is equal to mu times N. So what I'm going to do now is take the partials with respect to P. So we're going to get del G, del P, and I'm going to get del mu, del P. Of course, N is not a function of pressure. Alright, cannot be a function of pressure. But we already have those partials here. So what we're going to have is as follows, that the volume is equal to the number of particles, capital N, times del mu del P. Alright, del mu del P. But next thing we need to know is that the ideal gas is that PV is equal to nKT, or V over N is equal to K times T over P. So that's our little aside, or how we get from what we have at the moment to the ideal gas law. That means that we can rewrite what we have at the moment as the following. We're going to have del mu del P is going to be equal to V over N is going to be equal to K times T over P. Alright, now what we're going to do is we're going to integrate all of this. So this is a pretty straightforward and pretty usual integral, and it turns out to be as follows. We're going to get del mu integrated between mu 0 and mu. Let's assume that the chemical potential can change. Then we're going to get KT integrated from P0 to P, and we're going to have dP over B. Notice we've gone to total derivatives this time because we can, as in there are no partials, I suppose, on these sides. So I'm going to just bear with me. I'm going to rub out all this and go back to the start. I'm sure that's an integral you're well able to do at this stage. So that integral anyway turns out to be mu minus mu 0 is equal to KT outside the natural logarithm of P minus the natural logarithm of P0, or is KT log P over P0. Alright, so that's what we have. So another way of writing this is that the chemical potential that we have at the moment is the chemical potential which we started with plus KT, the natural logarithm of the ratio of the current pressure and the initial pressure. Okay, now that's it. That's the chemical potential of an ideal gas. But I'd just like to do a small bit of analysis of this. First of all, if we look at what we'll say the chemical potential is a function of. So we say that the chemical potential is a function of temperature and pressure. Okay, we'll say that mu 0 is also a function of temperature and pressure. And it's equal plus, we'll say KT, the log of P over P0. Okay, so we know of course pressure is just a function of pressure. Now, let's look at a small bit of an aside. We know that pressure is force per unit area. Okay? Aside to that, we know that mass is equal to density times volume is equal to density times the area times the length. Or what we can say is that the area is equal to the mass divided by rho times the length. Alright, so if we sub this back in up here, what we're going to get is that the pressure is equal to the force divided by the mass multiplied by the length multiplied by the density. The conclusion here is that pressure is proportional to the density. That's the conclusion here. So, going back to the equation that I have in red, this particular equation indicates how the chemical potential varies with pressure, or because pressure is proportional to density, it also indicates how the chemical potential varies with density. So this is the chemical potential of an ideal gas. Thanks for watching. Please pass it on to your friends, subscribe to my channel, and you might also visit universityphysicstutorials.com.